So thank you very much for the very kind introduction. I should say that, I mean, Jared said that I run this information initiative at Duke. One of the good things about being early to the data science space is you get to choose the good acronyms. So the acronym for the information initiative at Duke is IID. And there's a story that I convinced the provost, who was a non-quantitative social scientist, that information was going to change every department in the university and that we ought to have an initiative on data science. And a couple of years later, I'm talking to Peter, the provost was Peter Lang, and I'm talking to Peter, and Peter says, Robert, he says, did you realize that IID has another meaning? I said, of course not, Peter. So, 50 years of learning from data. The title is inspired by an essay that David Donahoe wrote recently about 50 years of learning from data. And I wrote this talk for David's 60th birthday conference. And I thought it would be a good fit here, too. So this is, you see David here in the top left. And the point that I'd like to make about this slide is that graduating from Princeton in 1978 were three famous data scientists. David, of course, is a famous statistician. Eric Lander is famous for managing the Human Genome Project, and he's the founding director of the Broad Institute in MIT and Harvard. And Tom Layton founded Akamai Technologies. So these are all data scientists. They're very different data scientists. And I wanted the slide to communicate that there's all sorts of different sorts of people that are data scientists. 50 years of data science. David, when he was a student at Princeton, was a student who spent a lot of time with John Tukey. And John Tukey spent a lot of time thinking about statisticians and what they did. And this beautiful quote from Tukey says, "For a long time I've thought I was a statistician. But as I've watched mathematical statistics evolve, I've had cause to wonder and to doubt." So there's always this tension in statistics between making these beautifully complex mathematical models and learning from data. And Tukey was very much the learning from data sort of statistician. A little later, John Chambers. We're now almost so familiar with R that we've forgotten a little bit that before R there was S. And John Chambers was the lead author of S. And John Chambers, too, was thinking about the statistics profession. In some sense, he's also thinking that perhaps traditional statistics had developed this unhealthy fascination with unhealthy mathematical fascination of sorting outliers in small data sets. I have to say that I grew up in Bell Labs, and I knew that statistics was important because there were two statistics departments in the Mathematical Sciences Research Center, and there were only, I think, 6 departments altogether, so I knew it was very important. And they were all Bayesian. And so I grew up thinking that all statistics was Bayesian. And it was only later when I went into academia that I realized it was different. Anyway, David, in his essay on data science, is also wondering about this balance between learning from data and making models. I like this book. It's a book about Bell Labs. there's quite a few books about Bell Labs, and many of them I don't like. The ones that I don't like are the ones that celebrate randomly turning over stones, because I think that's not actually what happened. I think what was special about Bell Labs was that there was a company, AT&T, and there was a grand challenge, which was actually making telephony work from one coast of the US to the other. There was a great fundamental research program, but when stones were uncovered and there were things like the transistor lying underneath them, people thought about how they could be used to advantage in this mission. And I think that, that Gertner really does a good job in this book of doing justice to that way of organizing. Now, telecommunications has actually changed a lot from when Shannon joined Bell Labs in 1941 to how it looks today. I've been told that I should curb my enthusiasm for walking this way. So, but over on the left-hand side, if you imagine telecommunications in 1941, what does it look like? I've used a triangle to represent it. And you see most of the green, most of the money, most of the mass is at the bottom of the triangle. So telecommunications in 1941 is all about gear. It's all about network infrastructure. As you go further up, there's a little bit of information that has to do with managing networks. And there is a super tiny bit of software on the top. Today, this triangle was still a triangle, but it's completely turned around. There's a little bit of commodity infrastructure at the bottom. There's still quite a bit, well, there's more information about network management, and there's an enormous amount of software at the top. And so the most important thing in telecommunications is the top. And, you know, sometimes people whine about the death of Bell Labs and how that means that research in telecommunications has fallen away. And I think it just means that you have to think about research in telecommunications properly. I mean, if you think about Google and Facebook and Amazon, that's really telecommunications for today. And there's more research going on in that field than there ever was. So I don't think it's so sad after all. Jared said something about, so when Bell Labs and AT&T split in 1995, I made this decision not to stay at Bell Labs where I'd worked on physical layer stuff. I mean, those of you who are old enough to remember these modems that burped and squeaked at you, those run off some of my signal processing patents. I also did disk drives for computer memory. But I thought it would be interesting to go to a services company like AT&T and to try and put together a research organization for a services company. And this was a time before Google, before Facebook, when people didn't really think that services organizations actually needed research organizations. So it was a bit dangerous. And what we did at AT&T was to go out into the company and bring all of the data that we could get our hands on into the research organization. What we did was we created a sandbox where researchers could play with data, where they could design proof of concept prototypes. And I think that when you try and design a research organization like that, it has to work in two directions. So it has to deliver valuable stuff for the company. So stuff, for example, that Jennifer Rexford, who's now chair of CS at Princeton, she designed these beautiful systems at AT&T that use traffic to identify router misconfigurations. Her code still runs in the AT&T network every night. So it has to work for the company. It also has to work for the researchers. So if I look at the people that worked at AT&T Labs in the sort of 1995, 2005 timeframe, I counted 5 of those people that got elected to the US National Academy of Engineering and got elected at age 50, which is quite something. So it's got to work in 2 directions. It's got to do stuff for the researchers, and it's also got to do stuff for the company. This slide also says something about what is data science. So data science is about going from data to some kind of decision. It's not just one thing. It's about getting data. It's about staging it and storing it. It's about analyzing it. It's about visualizing it. It's about putting together a chain. If you don't have one of the links in the chain, you don't have anything. But if you have the chain, then anytime someone arrives with data and some knowledge about what that data means, you can do stuff. And so that's the view that we developed about information. So we organized AT&T research around 2 questions. What information do you need to operate and compete? And how is the information obtained and applied? In some sense, we used to be a manufacturing economy. Now we're a services economy. Success in the services economy is about information at scale. Profitability in the services economy is really simple. You get to be bigger than your competitor, and you use automation to drive cost out of your operations chain. If you can discover stuff consistently before your competitors and act on it with more insight, then it's really difficult for you to lose. Okay. This is propaganda, in a sense, and you have to create stories to support the propaganda. So the idea is that if you do big problems, then those problems will illuminate the research frontier in the individual disciplines. And so there is when you work on these projects, you connect operations, systems, and research. And maybe I'll we're going to see what, oh dear. Tell stories. I should tell this story. So this is my point about, this is my point about manufacturing economy. This is a rather snarky comment from David Donahoe. When David Donahoe says, "What's a data scientist?" And he says somewhat snarkily, "A person who's better at statistics than any software engineer, and better at software engineering than any statistician." It's a great definition. 2 examples from AT&T are Rick Becker and Alan Wilkes. Maybe I talk a little bit about them in the next slide. So Alan Wilkes is on the left, Rick Becker is on the right. Rick Becker was one of the principals in S with John Chambers. He did dynamic brushing in S. These 2 guys, wrote the system that AT&T uses to generate all of its bills for wireline and wireless calling in the US. Now, this is highly unusual because if you know anything about industry and research organizations in industry, researchers in industry are not usually trusted to write software that has to do with the financial health of the company. So how did they get to do it? This was a really tough time in telecommunications. Costs of calling was going down. Company was laying off all sorts of development organizations. We were the only people standing. The development team had quit because they couldn't do it, and we got a chance to do it. We got a 12-month window, and these two guys, supervised by Darryl Pregobon, who's a well-known statistician, built the system. They had 50,000 straggly lines of C++. They turned it into 5,000 lines of C. We ran their system in parallel with the legacy system for 6 months. Every time it gave a different answer, we drilled down. They were always right. So it's important, actually, to remember that this is before Google. And actually, I like to think that one of the reasons that Google went after both Corinna, who's here on the top left, and Darryl, is the work that they did at AT&T. And actually, if you went to Google pre-IPO, you feel really good about that decision. And both of these guys went to Google pre-IPO. When I ran the networking center at AT&T, we had a pizza lunch every 2 weeks. And at the pizza lunch, we had a talk. And there was only one rule about the talk. And the talk was, well, 2 rules. It had to last for 20 minutes. And you could only talk about a problem that you didn't know how to solve. And what happened was that Corinna talked about, so there are about 350 million calls a day in North America. There are about 350 million telephone numbers. And the problem that Corinna couldn't solve was how did you generate signatures on those telephones, and how did you maintain them over time? We needed to do this because we needed to control fraud on our network. And Ann Rogers, who's now at Computer Science at Chicago, Kathleen Fisher, who's now at Google, they developed a program-specific language called Hancock, which does signatures at scale. And there's a great story about this and about how this kind of activity works for researchers. So they wrote this paper on Hancock, and they sent it to KDD. And the first time they sent it to KDD, it got rejected. In fact, the reviews were pretty brutal. Basically, the reviewer said, "We don't think this is a problem. What are you doing?" The next year, they didn't change much at all. They just resent the paper, and they got the best paper award. So the fact that they were working on this problem distinguished them as researchers. I'll say a little technical thing. What are signatures? Signatures are telephone numbers. This is, what's a signature? First of all, I mean, David Donahoe in his essay on statistics says simple statistics are better than complicated statistics. So when you call, how long you call, which region of the world do you call, these are elements of signatures. One of the things that we did was, so you've got a graph, 350 million nodes, which is connected. The connections change. If I give you a number, how do you generate the calling community centered on that number? So we developed code that was able to do that in 20 seconds. We, of course, don't store the graph. What we do is we store a list where you have for each number the 10 numbers that it most commonly calls and the 10 numbers that most commonly call it. And we create the graph on the fly. So, little technical thing. All right, so that's a company. You say, okay, companies have lots of resources. They have big data sources. What can you do at universities? So here I'll tell a story about, I think that there are opportunities. So this is an opportunity in health. We in the United States have this fantastic health system. We spend twice as much on it per capita as you do here, and our outcomes are not as good. And so that creates an opportunity. And in fact, you know, part of the opportunity is developing, we think, is developing apps that enable people to take better care of themselves. because that will reduce the healthcare costs for the system. This is, there are many aspects of this that I would like to feature. Oh dear. So this is an app for understanding autism. So autism is a behavioral condition. It's about inability to transfer attention or emotionally engage. Typically, we diagnose kids when they get to be age 5 if they live close to major medical centers and they have pushy parents. When they come to the Duke Medical Center, we show them videos, and they have professionals who watch them, and they screen them for attention and emotional engagement. This app was developed by Guillermo Sapiro, who's an engineer in our electrical engineering department. He's an expert on computer vision. And Jerry Dawson, who was the CTO of Autism Speaks. And what Guillermo did was he took the videos that the kids watch in the Duke Health Center and he put them on the iPhone. And he uses the camera in the iPhone, which is a pretty crappy camera. And he tracks attention, and he puts little landmarks on the faces to infer emotional attachment. And the results that we get are consistent with the most professional screeners. And this is an app that was co-developed by Apple. Jeff Williams, who's the #2 guy at Apple, is particularly interested in this app. And we have learned a lot from working with Apple on this app because they really understand user interfaces. Our engineers talk to their engineers, and their engineers say, this pixel has to move 2 to the left. And we think, what are you talking about? And then we move it to the left, and it looks much better. So they're really good at this. This app is released in the US, it's released in China. I think that there are many apps like this that are possible and could be really useful. What's this got to do with research? That's just got to do with research in statistics, because in statistics we're used to designing surveys with randomly selected samples of people. These are not randomly selected samples of people. These are people who select themselves. And understanding how we design apps in that world is, I think, really interesting. And it's a new frontier, a new research frontier. I mean, these applications, just because they're useful, it's not enough. They actually have to illuminate something new from a research perspective. Okay. Let me talk about undergraduates. So this is IID. We're on the 3rd floor of what used to be a chemistry department. We have about 25,000 square feet. We have about 85 graduate students and postdocs. They're from computer science and electrical engineering and math and statistics, and they're all mixed up. And every summer, we run this program called Data Plus. When I'm describing Data Plus, I describe it like this, okay? Why do students come to Duke? Now, when the faculty are feeling particularly good about themselves, they say, oh, they come to Duke because of the quality of the faculty. We actually know that that's really not true. They really come to Duke to be surrounded by students who are just as smart and interesting as they are. And then their educational experience doesn't take any advantage of that. I mean, they take classes, we grade them, we basically do triage on them. And so what we've done with Data Plus is to create an opportunity where they work together to solve problems and they learn from each other. And so that's the main message in the Data Plus. So if you're going to run one of these programs, you have to get the right people to coordinate. So I'll give you an idea of the scale. So there's 70 students, 25 projects. Each of the projects is managed by a graduate student or postdoc. We like to have external clients. We know that in the beginning, actually, one of the job of the graduate students is to manage this interaction. So clients are unreasonable. They think that their data's perfect. Students can do certain things. They're not good at doing other things. The job of the manager, in part, is to align expectations. It's really important. Actually, if you're thinking about professional development of graduate students, if you're a graduate student and you're hired by a company, that company's going to want you to run a team. This is an experience of running a team. Actually, if you're an undergraduate, well, I'll come to that in a minute. So anyway, the two people here that coordinate it, Paul Bendich and Ashley Valenti, they're really good at coordinating. I mean, so in the 10-week period, the students will present about their project twice. The first presentation is, this is what I think my project is. The last presentation is, this is what it's become. And they give presentations, and Paul has this very nice way. You have a student speaking, and he'll say, you know, you don't really know R, do you? That young woman over there, she really knows R. And this afternoon at 2:30, she's going to teach you about X, Y, and Z. And he does it in a very charming way, and it's very, very effective. All right, this is our picture of what is data science. So the columns in this matrix are the 25 projects from, I think, 2016. And what we did was we broke each of the projects down into 3 buckets. Getting data, maybe cleaning it, analyzing it, visualizing and communicating it. So you can see that all of the, I mean, there are no completely full columns, but to be successful, a project has to have some representation in each of these. So when we think about training data scientists, we think of students that are going to be experts in one of these, but who know how to put a chain together in order to do things. What we believe, what we hope is true, is that students that come through this program, they can actually, when they get attached to a faculty research program, they're actually more effective because they can bring in other stuff in ways that perhaps they couldn't before. This is we have fantastic demographics in this program. So this program, students apply. So we have like 300 applicants for 60 spots. And when we look at the applicant pool this year, 60% of the applicant pool were women and underrepresented minorities. And so that's what the participants look like. We don't do anything special to increase that. We also, our sweet spot is first and second years. Now, you can say, you know, research, only postdocs can do that. And actually, first and second year undergraduates, you know, these projects, you want them to know, you know, it's important that they know some R, some Tableau, some Python. Not all of them know that stuff. But in that group of 70, there are people who know that stuff, and they teach each other. All of these students are in the same space. It's actually hard for students who are this age to admit to faculty that they don't know something. It's much easier for them to admit to peers. The other thing I'll say about this picture is that there are some weird majors over on the right-hand side. And this is perhaps a little bit of a feature of the US system. So what happens here is the students indicate which of the projects they're most interested in, and they drop their CVs. And so we get to see whether they can code or not. And what we saw over here was young women who had come to Duke. They had great math SATs. They did really well in their math CS and stat courses. And then for some crazy reason, they chose to major in art history. Now, you don't have this majoring problem here. Okay? But when we looked at their CV, they actually know how to code. And so here they're coming back and they're doing data science. One of the reasons I put this slide up is that this national conversation about STEM is always kind of depressing because it's always about how badly you lost. You had all of these smart people and then you fritter them away. And here we're actually having a conversation about attracting new people in, which I think is kind of important. I should say that this first and second years is really a sweet spot, because if you're a rising senior at Duke, you're really interested in scoring that internship with Google in the summer of your junior year, because they might make you an offer when you graduate. But if you're a first-year student, you're not really competitive for that internship, because those juniors, they know more than you do. But if you do this program, then you will be super competitive when you get to become a junior. That's the idea. This is a Provost Slide, which is, don't think of it as 10 weeks in the summer. Think of all the planning that has to go into it. I mean, we pay our students $5,000 for 10 weeks. They have to find their own housing. So this program probably costs about $500,000. I get about 100,000 from the provost, so I have to go and find 400. So that's one of the jobs that I do throughout the year. Many of these projects involve confidential data. And so we have a protected research data network. So actually, if you do health projects, you don't want to have this conversation with your health system about where the data lives, because the data isn't moving from the health system servers. And so what you have to do is spin up virtual machines with certain capabilities and not with others that go visit the data and do stuff. So that's what we do. Also, if you're looking at confidential medical records, you have to be trained. So there's a whole IRB process that you have to go through. And that has to be gone through before the students start. So we do all of that stuff. What are some examples of projects? Well, I'll talk about this one here. This is interesting. So gerrymandering is in the news in the States. So in the States, what happens is if you're in a state like North Carolina, where one party controls the legislature, they get to set electoral boundaries. And they do so for partisan advantage. Now, I have to say in North Carolina, it's the Republicans that are doing it. But if you go to Maryland, it's the Democrats that are doing it. So it's a bipartisan thing. And this was actually a Math Data Plus project, where what the students did was they explored every way of drawing these boundaries that met the rules that the Electoral Commission, the Electoral Commission has rules that you can't divide things in this way, in certain ways. And they were able to ask the mathematical question, which was, how unusual is it that in a state that splits 50-50, the congressional delegation splits 10-3? And so you can get a mathematical answer to that question. And actually, the undergraduate students and the graduate students who worked on this project are now part of a Supreme Court brief. So for undergraduate students, that's really a cool thing. You get to be part of arguments to the Supreme Court. Over here, this is a little bit more pedestrian. We don't have any idea of how much solar energy we have in the States. There's no record of who buys solar panels, where they are. And so what this project did was they took satellite imagery and they learned to recognize solar panels. And so you could infer something about solar penetration. Maybe I'll come back. No, I won't. I'll come back to this one. This is a medical records thing. This one here is kind of interesting. If you're an African-American woman and you type style into Google and you ask for images, you'll get 50 images. They'll all be very thin, very white women. Probably 25 of them will be Taylor Swift. And what this project was about was, could you use the Google search facility to aggregate content in a more appropriate way, or in a different way? Data Plus is a little bit subversive. Actually, one of the things that said to Peter was, our provost, was this data revolution, it's going to happen at a rate that's faster than you can change the faculty. So you have to find ways of teaching old dogs new tricks. And this is an example. Emily Bernhardt is a very distinguished ecologist at Duke. She wasn't very quantitative. In 2015, Matt Ross, who was her PhD candidate, who was also not very quantitative, had a group of students that visualized a data set about mountaintop mining in Appalachia. The visualization was stunning. I mean, Emily got a $6 million NSF grant. She got featured on the front page of the New York Times. Matt Ross just got a job at Colorado State. And he says here, it completely changed her research program. And actually, Emily would say, it completely changed my research program too. So this is a way, so you can infuse change into the faculty up from undergraduates to graduate students. And if you ever think that your experience as a graduate student in the sciences is awful and unfriendly, you should go and talk to a humanities student, as their experience is miserable. If you're a humanities student, the first feedback that you can get on your work is perhaps when you submit your book for publication after 7 years as an assistant professor. So they don't have this tradition of exchanging ideas. So this is something here. And here, this is Duke Health. And here, one of the things that I just want to show you, I'm going to encourage you to check out our website, and I'm going to see if I can remember to do this properly, is we have 25 teams. One of those teams is a student videography team. So they get paid $5,000. There's 2 of them. And what we ask them to do is to tell stories about us. They get to decide, we give them some what we think are stories, but they have to choose the stories and they have to tell them. And so they make 2-minute videos. We made the calculation that we could have me describe the program, or we could have students describe the program. And we decided that the second would be way more compelling. So, let you judge.
So the benefits of using data to help push medical research forward, simple answer is you couldn't answer the questions that we need to answer today if you didn't have data analytics. The questions that are facing us are the ones where a statistician alone can't do it or a computer scientist alone can't do it. We really need the skills that we each bring to the table.
And we use our data set to create this graph.
Data Plus is the first program that I've come across that takes students purposely from different disciplines and brings them together.
I'm a rising junior and I'm majoring in computer science.
I'm a master's student in the Department of Biostatistics.
I just graduated with a degree in biology and global health.
So our project is called Diagnosing Diabetes and Predicting Complications.
We're trying to predict which groups will get these complications and how we can best target therapy.
We're using t-SNE clustering. What we're trying to do is from these clusters, we're trying to create a predictive model.
Built through an INET model, and that's a complex regression model.
And this is the INET. So which one am I going to use?
This program is very collaborative. We have so many mentors.
I think it might be beneficial to make those into functions.
I've really enjoyed working with these students. They're extremely hardworking, really self-motivated, very interested in this work.
It's like 500.
Each one of them really brings a different kind of aspect to the team.
In global health, I think we learned a lot about the idea of health disparities and trying to find therapies that target specific groups.
Me and Lily both didn't have R, and having Angie, who is a master's student in stats, has been really helpful.
It shouldn't be like this.
Okay.
I am a computer science major, but I'm also really interested in the health field.
Type 1 diabetes is usually diagnosed when you're a child and is not caused by any lifestyle choices.
To be able to take young students who are not even 20 yet and expose them to that type of work and collaborative research environment is invaluable.
I've loved hearing about the other projects, about how you can apply computer science. I almost have ideas for things I could do in the future.
I'm responsible for putting together funding for many of these projects. And one of the sets of people that we hit up are Duke institutions. So we've done a couple of projects with Duke Development. These are the people that raise money. We stratified their entire alumni base. So if somebody gave a bunch of money, they can pull up 20 people with the same characteristics and go after them. This one is parking. So parking wanted to think about a parking product that they could offer faculty and students where it would cost a little bit less, but they would have an opportunity to redirect you to lots if some were full. And first they had to visualize how people parked. And we have these automatic barriers that go up and down, and they collect data. And they thought that this data was really good. And 2 weeks into the project, Mitchell comes up to me and he says, I'm really worried about this project. I said, Mitchell, why are you worried? He says, well, this lot over here, he says, how many people do you think were parked in it October 26th of last year? I said, I have no idea. He says, minus 65. So this was a big surprise to our parking administration. Towards the end of the project, Kyle gave me a call. He says, I'm really worried about this project. I said, why are you worried, Kyle? I thought it was going very well. He says, well, I'm just realizing, he says, that in 2 weeks' time, these students aren't going to be working for me anymore. And so actually, he had to put one of them on work study throughout the year. And he's just hired a data scientist. So it's actually kind of interesting. So when I talk to people about the value of this kind of thing, I make a comparison between companies and universities. Companies are really super at looking at the data that they generate and doing things differently. Maybe universities in the UK are much better than universities in the US, but we don't do any of that at all. And so when I talk about Data Plus in this way, I talk about transforming universities into institutions that learn. I think that's the last slide. We experiment with, actually I didn't quite stage this properly, but for these projects, we actually want to capture how students learn. So we invested in Slack. So students post, the projects are threads, students post to the threads, they talk about what they can do, what they can't do. Other students help them out. What we think is that through participating in this kind of experience, students create little networks that go on to help them as they navigate through the rest of their university career. That's the last snarky comment. All right, questions?